Hi, and welcome back to Topology. I should start by saying that I completely understand. I know some of you all are not able to do much work right now, and so you can uh, rest assured that I'll be flexible when it comes to turning in work. I know some of you are serving the country and taking care of relatives. Um, Let me know how you're doing, and I will be totally understanding. So, I'm going to start with going over some of the problems from Quiz 8, and I'll get out of the way in just a second. And there will be a Quiz 9, which is going to be very similar, and I'll post that after these notes. All right, so take a look at your Quiz 8 if you have it. And let's look at this mystery surface S. Now, I labeled some parts of this picture for you. Let me grab mine. We called this A, B, and C, those three edges. So notice that those letters are kind of arbitrary. We could call them anything else that we wanted to. And I also labeled for you the fact that it turns out all 6 corners are the same point. And that you can figure out logically. If you call this point x0, then it must also be here, because both of those start the same edge. The single arrow on that edge indicates that those edges are going to be glued together. But that means that this x0 starts the triple arrow edge. So that must be there also. And it keeps going. That's the end of the single arrow edge, which is also here. The beginning of the double arrow edge is also here. And the end of the triple arrow edge, which is also here. So they're all the same point. That means that each of those glued edges is indeed a loop. Starts at x0 and ends at x0. So the fundamental group pi 1 of S can be written as those 3 loops as the generators, and then one surface, one copy of D2, the disk, gives us a relation. And there's not just one way to do this, but the way that the picture suggests is to start on the left and follow A, B. However, after that, there's a C inverse, because we're going against the direction of C. Again, that's arbitrary. We could have chosen to draw those arrows in the opposite direction. What's really important is that this triple arrow edge and this triple arrow edge, when glued together, are going to have to be glued with a flip. That means that if I call this C inverse going against the arrows, the triple arrow, just for convenience, that'll allow me to see that going around the other side of the disk. So the first was to travel around the top. I'll put like a sort of a dark arrow showing that I just went that way around the disk. If I go the other direction, now this arrow is not indicating that I'm going to be doing any gluing. Those two are just 2 routes to take around the outside of the disk from one side to the other. So ABC inversed around the top turns out to be equal to following C, this time with the triple arrows, then B, and then A around the bottom. So if you want to label these also, you can. And that's the first. It turns out, as you know, the answer turns out that these are homeomorphic spaces as the first fundamental group presentation. So second, we have here, separate those, a picture which is going to be the projective plane, two-dimensional projective plane, connected sum with the two-dimensional torus. So I'll label them like they are on the quiz. In order to make the projective plane, I used a single arrow to glue the left side to the right side with the flip, and I used a double arrow to glue the top to the bottom with a flip. That's a picture of P2. To make the torus, I needed some different arrows, so I'll use a triple arrow on the left, and it glues directly to the right hand side with a triple arrow, and then a quadruple arrow on the top glues directly to a quadruple arrow on the bottom. But in order to make the connected sum, I need to cut out a disc from both and then reattach them. Conveniently, I cut a disc out starting at the corner, and to make sure that I attach those two discs exactly the way they're cut out, I'll put an arrow showing that they're attached with that matching orientation. So that's a missing disc. If you want to shade in the rest of it, you can. It's not totally necessary, but I will. There. That shows the connected sum of P2 and T2. Now, here's where it got a little bit tricky. The first thing I did was to label those edges, and then we calculated the Euler characteristic. So just for illustration, I'll calculate the Euler characteristic of P2 pound T2. And the edges being labeled, I'll leave that off for now. It turns out to be a point of confusion when it comes time to calculate the fundamental group. The Euler characteristic, however, we can see there's two copies of D2, two disks. Those are the big squares. And there are a bunch of different arrows, but we only count them once for each kind since they're glued together. And we do need to figure out how many corners, how many points there are, how many copies of D0. So again, we can call this X0. And did I do that on this page? Nope. Skip that. I called it Y. And I called this one X0. So Y is the beginning of the single arrow here, so that's also Y. Whereas X0 is the end of the single arrow. So that's there. Compare that to the hexagon on the other side. We did not discover logically that the four corners were all the same. However, this X0 must be the same as this point because I'm gluing those two cut out circles together in order to make the connected sum. And then that must be the same as this point because it's the end of a triple arrow, which must be the same as this point because it's the end of a quadruple arrow, and must be the same as that point. It's the beginning of a quadruple arrow and the beginning of a triple arrow. All right, so now we can see how many of each there are. There are actually only two zero-dimensional discs, 2 points, 2 corners. And all of the one-dimensional discs, the line segments, come in pairs. So there's a single arrow, a double arrow, a triple arrow, a quadruple arrow, and also the cutout excised disc with the sort of clear arrow drawn on it. So that's a 1, 2, 3, 4, 5. Then there are 2 shaded discs. So that comes out to a -1. Now, finding the fundamental group. Oh, we should probably do the Euler characteristic of the hexagon too. Of course, it came out to -1 also, but I can squeeze it in here. When you look at the hexagon, there are exactly 1 corner. All of them are labeled x0. There are 3 kinds of arrows coming in pairs, but they're glued together, so. And 1 disc. It's the hexagon, the entire thing. 1 disc, 2-dimensional disc, that is. So that also came out to be equal to -1. Alright, so now pi1 of this picture. So pi1 of P2 connected sum T2. Now we have a little problem when we look at that first half, the copy of the projective plane. And that is, those are not loops. The single arrow and the double arrow, those edges aren't making loops. This one is, right there. And that one I called C. And C shows up in 2 places, so I'll label it twice. But to make a loop, I'm going to have to go all the way from one corner to the other. So I actually have to use both the double arrow and the single arrow. So you can follow that to make a loop. That's 1 loop. So that's why I decided to call it B. That's a generator of the fundamental group. Compare that to in the first picture, however, I did draw a pathway going from one side of the disk to the other. But that pathway used all 3 loops, A, B, and C inverse. This, there's only 1 loop, so I have to call it just B. I also have C. That's a loop. And then I look over at the copy of T2, and it does have loops. So let's see, I think I decided to call this one D and this one F. Those do go from x0 to x0, so put in D and F here. And now there are 2 disks, so we'll have 2 relations. From this disk, if I follow along the top, I have B. If I go along the sort of left and bottom of this disk, I didn't write this in for you on the quiz, it's B inverse. Okay. So that means it's because I'm following that black arrow. And let me make sure you understand these curves following this black arrow or this one mean that I'm following along the double arrow and then the single arrow for that B. And that's why this is B inverse. It goes against the grain, against the single arrow, and then against the double arrow. And those curves were actually lying right on top of the double arrow and the single arrow, or just a little bit off. Of course, everything is up to homotopy, so we're allowed to slide the curves around a little bit. So now I have a relationship, a relation between some of these generators for that first square. The easiest way to write it is that going C and then B is the same as B inverse. Well, one way of writing it. For the second disk, the second square, one way of writing it is that if you go, let's see how I put it here. Yeah, either way. If you go D, then C, and then F, in other words, start at this corner, follow all three of those loops. Now they're all loops, so I need to write them all down. That's the same as going first along F and then D. No inverse is needed if I follow them in those directions because they're all going in the same direction as the arrows. So I get the other relation is, I'll put a comma there, DCF equals FD. Okay, so of course this was very suggestive, and we did at the end of the quiz see that S is homeomorphic to P2 pound T2 by seeing a cutting diagram. But the interesting thing that I'd like to do next is to see that these two presentations of the fundamental group do give you the same group. I'd like to see the group isomorphism.